Good afternoon. This is Professor Shannon Gracie, and we'll be covering section 5.3 from Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan. So today we'll be looking at how we evaluate exponential functions, graph them, defining the number e, and solving exponential equations. So you should have seen a lot of this in intermediate algebra. So now it'll just be all sort of condensed into one with some more interesting, fun math stuff going on. So go ahead and pause the movie and warm it on up. Okay, let's see how you did. If we come over here, you can see that this is quadratic in form. So if you let u equal to the quantity x squared minus 2, and then we'll end up getting probably a couple solutions potentially, so we'll just leave that over there. And so we'll end up with u squared minus u, and then if we is equal to 6, and then if we get the 6 to the other side, we'll have this equivalent equation. Now we can factor this. We'll have, let's see, I believe u minus 3 times u plus 2 will give us the factorization we need. And using the zero product property, we have these two linear equations. So we'll get u is equal to 3 and u is equal to -2. So coming back over here, looking first at u equal to 3, and then over here we'll do u is equal to -2. Notice that we're in the complex number system, since we can have solutions with I in them, complex solutions. So we'll get 3 is equal to x squared minus 2. So basically, wherever I saw a u, I put 3 in this one. So then, adding 2 to both sides, we get 5 is equal to x squared. And then, square rooting both sides, we get plus or minus root 5 is equal to x. Now, coming over here, we'll have our other solution, which was -2 is equal to x squared minus 2. So here we have, in for u, I'm putting -2. And then, let's see, next step, adding 2 to both sides, we get 0 is x squared. And then evaluating the square root of both sides, we will get 0 is equal to x. So our solution set will be, actually in the real number system for our solutions, we'll have -√5, 0, and √5. So notice that we have a multiplicity of 2 for the solution x equals 0. How'd we do? We do okay? Awesome. All right, so here we go. Next up, we're going to use the calculator to practice evaluating exponentials, and also to kind of look at what happens, right? So here we go. If you take a look at, let me get our graphing calculator up. So here we go. Just sort of a note here. Let me clear this stuff out. If you just take a look at the square root of 5, because that's what we're heading towards here, do you see that's approximately 2.236067977? So these are all getting closer. These numbers here, do you see, are all getting closer and closer to √5, the numbers that are in the power. So the first one, 3 raised to the 2.2 gives us a result of, let's go to the nearest, like 4 decimal places. So that's going to be approximately 11.2116. These will all be approximate. All right, and then the next one, 2.24. So second entry, and then we'll change that to 2.4. And then we'll get, let's see, 13. Oh, not 2.4, my bad. Second entry, it was supposed to be 2.24. Thought that was a long ways away. All right, so we'll get 11.7153. And then next up, we're doing 2.236. $11.6639. And then we'll have, let's see, what's our next one? 2.2361. 2361. 11.6652. And here we go. This last guy. So just so you recognize, the first numbers we were evaluating at these we were raising 3 to rational numbers. So this last one is we're raising 3 to an irrational number. And so this is kind of where we're going with this. So we have the square root, whoops, of 5. And we'll get 11.6648 approximately. How do we do? You used to doing the evaluating exponentials on your calculator? Awesome. All right, so here we go. Laws of exponents. So basically, we've talked about laws of exponents for integers and for rational numbers, but now we're talking about the laws of exponents for any real number. If you recall, irrational numbers like the square root of 5 are real numbers. So here we go. If S, T, A, and B are real numbers with A and B both greater than 0, then A raised to the S times A raised to the T is equal to A to the perfect S plus T. What about A to the S raised to the T? Good, it's going to be A raised to the S times T. And then remember that 1 to the S is equal to, good, 1. And A to the negative S, therefore, will be equal to actually, let's do, that's the same as A to the 0 minus S which gives us a to the 0 over a to the s, which is just 1 over a to the s. So you should have remembered all this from earlier stuff. And then if you have a times b raised to the s, that's equivalent to a to the s times b to the s. And I probably should have put this earlier, but a to the 0 is equal to 1. So that's just sort of a reminder of the laws of exponents. So here we go. Exponential growth. Suppose f has the following properties. The value of f doubles with every 1 unit increase in the independent variable x, and the value of f at x equals 0 is 10. So if you write that in function notation, f at 0 is equal to 10. So let's take a look at what happens here. So we probably don't need all of these numbers, but we can just take a look to get a trend here. So we know that f at 0 is 10, and we know that the y values are going to, they're going to double with every 1 unit increase. So f at 2 will be double 10, good, which is 20. F at 2 will be double 20, perfect, which is 40. And f at 3, you double this result, which would give us 80. And then doubling again, we would get 160. So let's check out, what a graph of this would look like. Excuse me. So here we go. Let's do our scale. Our scale would be if we have this go, the x-axis can just be plus or minus 10, but the y-axis, I'm thinking we should probably, we'll do the first 4 inputs, and we'll just go to 100. Sorry, these are in more, so that would be negative 10. This would be 10. This is x, and this is f at x, and this would be negative 100. So our first order pair would be at 0, 10. Second order pair would be at 1, 20. And then 2, 10, 20, 30, 40. And 3 was at 80. So that's 90, 80. Right? So we're going to end up having a growth function. So you can kind of envision if I plotted, 4, 160, it would be about up here. So we're going to have something that has very rapid growth. So let's see if we could get, a function going on for this. So like in a, function notation, we want to make an equation for this. So let's see what we have. Let's just kind of start off with what we have in our table. So we have f at 0 was equal to 10. And then we were talking about how f at 1 was equal to double f at 0, which was equal to 2 times 10. So let's write this as 10 times 2 to the 1. Similarly, f at 2 is equal to 2 times f at 1, which is 2 times, now I'm going to plug in that last thing we got for f at 1, which was 2 times 2 to the 1. So that's going to give us 10 times 2 squared. Are you starting to see a trend? So let's go on. F at 3 was equal to 2 times f at 2, which was 2 times 10 times 2 squared, which gives us 10 times 2 cubed. So we'll do one more, but I think you can see what's happening here. What's happening is that you have this constant ratio of 2 between each of the terms. So we can end up having, let me finish this guy off. That's going to give us 10 times 2 to the 4th. So what we'll end up having is this. Do you see how if you wanted to make an equation for this, they all have a multiplier of 10. So we'll have f of x is equal to 10. And then what power is that 2 being raised to? It's being raised to the same number as what's in the parentheses. Do you see that? So this guy here, these match. So if we follow that same trend, we would have 2 to the perfect 2 to the x. And that's our function. So here we go. Next page gives us an official definition for exponential functions. So an exponential function is a function of the form f at x is equal to c times a to the x. So in our equation before, what was our c? Perfect. C was 10. So a is a positive real number, and a has to be greater than 0, and it can't be 1, because when you raise 1 to a real number, you're going to get 1. And c is not equal to 0, is a real number. So the domain of f is all real numbers. The base a is called the growth factor. And because f at 0 is equal to c times a to the 0, which is equal to c, we call c the initial value. Because remember, a to the 0 is 1. Okay, so let's just take a look at, let's suppose we have this here. Play around a little bit. Okay, so let's check out what we have here. So suppose we have f at x is equal to 1/2 raised to the x. So if we find f at 0, that'll be 1/2 raised to the 0, which is, 1. And f at 1 is 1/2 raised to the 1, which is 1/2. F at 2 is 1/2 squared, which is 1/4. And let's do this guy. F at 3 will be 1/2 cubed, which is awesome, 1/8. So if we were to take a look at what happens to the ratio of these terms, right, of successive terms. So if you take a look here, so if you take a look at f at 1 divided by f at 0, you would get 1/2 divided by 1, which is 1/2. Now let's take a look at these guys. So f at 2 divided by f at 1 is, f at 2 was 1/4 divided by 1/2, which remember will be 1/4 times 2 over 1, which is 1/2. And I bet you can guess what you'll get here. F at 3 divided by f at 2 is 1/8 divided by 1/4, which would be 1/8 times 4 over 1, which is, again, 1/2. So it turns out when you divide the successive terms, so for example, f1 succeeds f0, then if you have an exponential function, you will get the same ratio, the same result. So this leads us to this theorem here. For an exponential function, f at x equals c times a to the x, where again a is greater than 1 and a is not equal to 1. If x is any real number, then f at x plus 1 divided by f at x is equal to, good, a. Or another way to look at it, if you multiplied both sides by f at x, then the succeeding term, successive term, f at x plus 1, would be equal to a times f at x. So it just depends on what you have and what you need to find. All right, so next up, let's determine if these functions are exponential. So here, the first one, remember the rules for it. You have to have a base that is good, positive, and not equal to 1. And your unknown needs to be in the power, right? So for part A, we certainly have it. Yes, our C is 1, A is good, 3. What about part B? No, it fails because, good, -4, A is -4, which is negative. So it does not work out. So no. What would happen with that is it would bounce back and forth. So what you'll find is you'll get sequences that will be alternating, and you'll learn more about that in I think you'll learn some about that in Precalculus 2 and then again in Calculus 2. Okay, so next example. Here we go. We're going to determine whether the given function is linear, exponential, or neither. So a linear function has a constant, good, a constant slope or average rate of change. And an exponential, we just learned, has a constant ratio of consecutive outputs, right? So here we go. Let's just kind of extend this chart, I guess. And so the first box we can say is the average rate of change. And then the next box can be the ratio of consecutive outputs. So here we go. So the average rate of change is the slope. So what we would have for this one would be 1/2 minus 1/4 divided by, good, -1 minus 2. So that's going to be 1/2 minus 1/4 is going to be 1/4 over -3, which will give us -1/12. Okay. So our next one would be, actually, let's see. Oh, my box is kind of funny. We don't need, actually, for this one, actually, let's do this. We don't need it columned like that. So this one is going to be, we'll do this. This will work better. So here we go. This was our first average rate of change. Now we need to do another average rate of change to see if it's constant. So this will end up being 1 minus 1/2 over 0 minus -1. So that'll give us 1/2 over 1, which is 1/2. So do you see, we can stop there working on average rate of change because these guys are not the same, so it's not linear. Okay? Now, the ratio of consecutive outputs, we'll work on that one. So we will have 1/2 divided by 1/4 is equal to 1/2 times 4 over 1, which is 2. Next up will be the next two y values. So we'll have 1 divided by 1/2 is equal to 1 times 2 over 1, which is 2. This is looking promising. Now the next two will be 2 divided by 1, which is 2, and 4 divided by 2 is 2. So it is exponential. So now our next job is going to be to find the equation for it, right? So what did we find when we were finding these outputs? Good, we found that A is equal to 2. So let's see. We also know that, so let's do our general thing. So f at x is equal to c times a to the x. So we have that a is 2, right? And we also know that f at 0 is c is equal to c, and we know that f at 0 is 1 from our table. So c equals 1. So putting it all together, f at x equals to 1 times 2 to the x. So our final result is f at x equals 2 to the x. And we're done. And so again, that's the c equal to 1 is our initial value. And then a equal to 2 is the growth factor. All right. So a couple more examples here. Let's see what we have for part B. So let's start with let's see if it's linear first. So testing if it's linear, we'd be looking at these guys, right? And we'd be finding the slope. So 3 minus negative 1 over negative 1 minus negative 2. So that would give us 4 over 1, which is 4. Because negative 1 plus 2 is 1. All right, so then we'll test these guys. So this is the average rate of change. And we'll have 7 minus 3 over 0 minus negative 1, which would give us, again, 4 over 1, which is 4. So it's looking promising for a linear function. So this is 11 minus 7 over 1 minus 0, which is, again, 4 over 1, which is 4. And then, lastly, 15 minus 11 over 2 minus 1 is 4 over 1, which is 4. So this is clearly linear. There's no need to test for, this is linear. There's no need to test for the exponential, for the constant ratio. So linear, the slope is equal to 4. And then I'm thinking, why don't we just use this ordered pair here, because that way it'll be the easiest ordered pair to use. So m is 4, and we have the ordered pair 0, 7, which is our y-intercept. So f at x is equal to mx plus b, since we have the intercept. So we'll get f at x equals, our slope was 4, and our y-intercept is 7, and we're good to go. Okay? All right, so last one. Let's see what we have. Again, average rate of change. We'll try this one first and see how it goes. So between these two guys, we'll have 1 minus 0 over 1 minus 0, which is 1. Between these guys, we will have 2 minus 1 over 4 minus 1, which is 1/3. So we know it is not linear. So now, ratio of consecutive terms. Or consecutive outputs, we'll say. So, actually, this is problematic because we can't do the ratio of the first two. Do you see that? Because we'd get 1 divided by 0, and that is undefined. So I'm thinking this will be neither. So then 2 divided by 1 is 2. 3 divided by 2 is just 3/2. 4 divided by 3. So this is not exponential. So our answer would be neither. And there's no need to find a function since we don't have something that is linear or exponential. All right, so now we get to sketching the graphs. So the first step is 2 to the x. So if we get some positive and negative values in here, let's start with the negative. So if we plug in negative 2, negative 1, 0, 1, and 2, that should give us a good feel for it. So f at negative 2, be careful, is 2 raised to the negative 2. So wherever we see an x, we're putting in negative 2. So that will give us 1 over 2 squared, which is 1/4. So our ordered pair is negative 2, 1/4. And then f at negative 1 will be 2 raised to the negative 1, which will be 1/2. And then f at 0 is 2 raised to the 0, which is 1. F at 1 is 2 raised to the 1, which is 2. And finally, f at 2 equals 2 raised to the 2, which is 4. So you end up having this graph. So we have negative 2 1/4 is about here, and negative 1/2, 0, 1, 1, 2, and then 2, 4. And if you wanted to do another one, you'd have 3 would give us 2 cubed, which is 8. So it turns out you've got a horizontal asymptote at the x-axis, and then it increases without bound. Okay? All right, so this next one, you've got a choice. You could plug in ordered pairs, right? Or you could use your knowledge about transformations. So with this one, this would be the graph of 2 to the x, which is being good. It'll be reflected across the y-axis, So it's your choice. If you want to plug in ordered pairs, you can. I'll show you doing it that way. Or just use your mad transformation skills. So g at negative 2 will be 2 raised to the negative 2, which is 4. And then g to the negative 1 is 2 raised to the negative 1, which is 2. G at 0 is 2 to the negative 0, which is 1. G at 1 is 2 to the negative 1, which is 1/2. And g at 2 is 2 to the negative 2, which is 1/4. Okay, so again, if we use that same scale, this is g of x, and this is x. So what will happen is at negative 2, we're going to be up at 4. That's too big of an ordered pair. Here we go. And then at negative 1, we'll be at 2. At 0, we're at 1. At 1, we're at a half. At 2, we're at a quarter. And then if we had done -3, we would be up here at 8. So as you see, it's a reflection across the y-axis from that original graph. Perfect. All right, how are these two graphs related? Well, we just said so. The graph of g of x is the graph of f at x reflected about the y-axis. All right, so then here's another example. A little bit different of a transformation here. So why don't you go ahead and pause the movie and do these graphs and see how you do. Okay, let's see how you did. This is G. Okay, so for the first one, we'll just do the same numbers we've been using. So f at -2 is going to be 3 raised to the -2, which is 1 over 3 squared, or 1/9. So we'll have the ordered pair -2, 1/9. F at -1 is 3 raised to the -1, which is, good, 1/3. F at 0 is 3 raised to the 0, which is 1. And f at 1 is 3 raised to the 1, which is 3. F at 2 is 3 squared, which is 9. So we'll have -2 1/9, -1 1/3, 0 1 1/3. So this is going to increase more rapidly, and then we'll be at 2 9. So it's got the same general form, except it increases much more rapidly. All right, how'd you do? Awesome. All right, so here we go. What's going to happen with this one? 3 raised to the x minus 1. So if we did this using transformations, this would be the graph of, let's answer the last question. This is going to be the graph of f shifted to the, good, shifted to the right by 1. The graph of g is the graph of f shifted 1 unit to the right. So actually, again, you can fill in the chart if you want, but let's graph this one using transformations. So it's supposed to shift by 1 to the right. So let's start with the order pair 0 1 that we had. Instead, it'll be at 1 1, shifting 1 to the right. And then we had an ordered pair at 1 3, so now it's going to be at 2 3. And then we had an ordered pair at 2, 9. So now that's going to be at 3, 9. And so then we'll have 0, a third, and -1, a ninth. Okay? And if you had, filled in the chart, that's fine as well. I used transformations. Point here. Okay, so here we go. This is what we found. If you have a positive growth factor, I'm sorry, A is greater than 0, my bad. If your A is greater than 1 instead of being a proper fraction between 0 and 1, then this is the type of graph you'll get. The domain is the set of all real numbers, or minus infinity to infinity, using interval notation. The range is the set of all positive real numbers, or 0 to infinity, non-inclusive, using interval notation. There are no x-intercepts because it never crosses the x-axis. The y-intercept is 1, or the ordered pair 0, 1. So the x-axis, or you can think of it as the line y equals 0, the horizontal line, is a horizontal asymptote. So as x approaches negative infinity, so what you'll learn in calculus is it's written like this. The limit as x approaches negative infinity of a to the x is equal to 0. This is when you have your a is greater than 1. And then fourth, we have f at x equals a to the x, where a is greater than 1 is an increasing function. And is 1 to 1. The graph of f contains the points 0, 1, 1a, and -1, 1 over a. And the graph of f is smooth and continuous. With no corners or gaps. So, okay, let's look back to what we just worked on at part A of each of these examples. So, notice that our A was 2 in this example 3A. So that is 2 is greater than 1. And notice how all the components that we just mentioned are there. As we move from left to right, the graph is going up, it's increasing. It's 1 to 1, and you've got those ordered pairs. A is 2, so you have -1, 1 over 2, right? 1 over A. You have 1 comma 2, which is 1 comma A, and you have 0 comma 1. Now, let's take a look at this part B. Okay, 2 to the negative x. We could also think of 2 to the negative x as 2 to the negative 1 raised to the x. Do you see that's the same? Because when you raise a power to a power, you multiply. But what is 2 to the negative 1? Good, it's 1/2. So you'd have 1/2 to the x. So notice what happens. It reflected across the y-axis. So as you move from left to right, this graph is decreasing. And you've got the ordered pairs, -1, 1 over a still, but your 1 over a is going to be 2. And you've got 1 comma a, which is 1 comma 1/2, and 0, 1 on the graph. So it's still going to be smooth and continuous. But now this is true for all proper fractions that are between 0 and 1 when you're dealing with an exponential. So let's fill in the properties for that. I think that's next. There we go. So the domain is still the set of all real numbers, or -infinity to infinity. The range is still the set of all positive real numbers, which would be 0 to infinity using parentheses, because it's not inclusive. There's no x-intercepts. The y-intercept is 1. Now, this is a little bit different. The x-axis, meaning the line y equals 0, is a horizontal asymptote. But that now happens as you're approaching infinity. So the limit as x approaches positive infinity of a to the x is equal to 0. Whereas before, as you were approaching negative infinity, that happened. So if you look here, see as you approach positive infinity, you're approaching the x-axis there. And over here, that first one, when a was greater than 1, as x goes infinitely to the left, you're approaching the x-axis. Okay. Finishing off, we'll have, so f of x equal to a to the x, where 0 is less than x is less than 1, is a decreasing function and is 1 to 1. The graph of f still contains the points -1, 1 over a, 0, 1, and 1 comma a. And the graph of f is smooth and continuous with no corners or gaps. And so we've already looked back at example 3, part B. Okay, so let's check out this situation here. So let's get our calculator back up. So if you look here, we're going to be considering this expression here. So 1 plus 1 divided by, we'll do the first one first, which is 1. We're letting n equal 1. 1 divided by 1 raised to the 1. And you see we get 2. So this guy here is 2. And then plugging in 2, so I'm just going to hit second enter. So plugging in 2 for n, we now get 2.25. And then starting to get bigger here. Plugging in 5 for n, we'll have 2.48832. Now go into 10. Let's see what we have. Still in the 2s. Now we're at 2.5937, 4246. 2.5937, 4246. And getting a little more extreme, now letting n be equal to 100, we will have 2.7048138829. And finishing it off, letting n be, what is that, 1 million did I do? Yes, 1 million. Let's see what we get. We get this magic number here, 2.71828187, approximately. These are all approximate. 81827. So this is a number that you deal with a lot in calculus. It turns out that if you looked at the limit as n approached infinity of this, we've just been plugging in values, you get the number e, okay, the number e. So actually I have all this written in here. So the irrational number e, which is approximately 2.718, is called the natural base. The function f at x equal to e to the x is called the natural exponential function. So the number e is defined as the number that the expression 1 plus 1 over n raised to the n approaches as n approaches infinity. So in calculus, this is expressed using limit notation as the limit as n approaches infinity of 1 plus 1 over n raised to the n. So it's kind of cool. Another way you can look at this expression is you can look at it as investing, what was it, $1 at a rate of 100% for 1 year. And so this is, your principal P times 1 plus 1 over R raised to the T times, is it T times R? Sorry, it's been a long week for me. But basically, if you use that, okay, so let's go ahead and sketch the graph of each of these exponential functions. So here we go. Again, we might as well let x be -2, -1, 0, 1, and 2. And so f at -2 is going to be equal to e raised to the -2, which will be approximately, I'll do this on the calculator. So let's clear this. And so to get to the exponential, you go to the second natural log, and then that gives you your e. And we're raising e to the -2. And let's see what we get. We get approximately 0.1, we'll just go 0.135. So we're going to get the ordered pair -2, 0.135. F at -1 will be e raised to the -1, which is approximately 0.368. So -1, 8. All right, and then this one we can just do regularly. F at 0 is e raised to the 0, which is 1. And then f at 1 will just be e to the 1, which is e, which is approximately, and if you ever forget, we'll do it on the calculator. So second e to the 1, you get, going to 3 digits, 2.718. And then f at 2 will be e squared, which is approximately 7.389. Is that what it was? Yes. Okay. So notice that since we have a base of e, and we've done the graphs, both graphs of, f at x equals 2 to the x and f of x equals 3 to the x, e is in between, the 2 and 3 as a base. So this graph should be in between those two. So we'll have f of x okay, so we got these ordered pairs. So -2, just over a tenth. And then -1, just above a third. And then 0, 1. And then 1, 2.7-ish. And then 2, 7.4-ish. 4, 5, 6, 7, about here. So then we'll have our graph. All right. Okay, again, this one, what is this graph going to look like? Every value we got for the y values that was positive will be negative. Do you see that? So the other way to think about this is, so used transformations. So how are these two graphs related? The graph of G is the graph of F, and what's happening with it? It's being reflected across the the x-axis. So here we go. Actually, let's make this smaller so you can see both graphs for the moment. So we've got so here you had the, let's start above here. So we had the ordered pair -2, +0.135. So it'll be -2 and then negative. So we'll have one about there. We'll have another one about here and then here. And then we'll have one at -2.718. And then at 2, -7.4-ish. All right. So then our graph will be like this. All right. Perfect. So exponential equations are next up. So here is one concept to use. If you have the same base and they're raised to these different powers, don't the powers have to be equal? Right? So one way you can solve exponential equations is to see if you can get them each to have the same base. It doesn't always work, but you can, this is one option. So here we go. Well, I have the same base of 8. Do you see that? So since the bases are the same, then you can equate the exponents. So this means that x has to be equal to -2. So that would be our answer. Okay, so here we go. The way you can verify your result using the graphing calculator is, if you go to your y equals menu, we can graph 8 raised to the x, and then we can graph 8 raised to the parenthesis -2. So that's the first one. Second one will just be a constant. We're not seeing it because it's really close to the x-axis. So if we go zoom in, And it's still not quite right because we need to go to the left more. So let's do our x minimum at negative, I don't know, -4, -5, I guess. And then our x maximum we can do at 5. And then I think this will be fine. Let's see what we get here. There's our graph there. Perfect. It's still kind of, actually, we'll do this. I don't think it needs to be this big. Let's see. Let's try this. I'd like to have a nicer picture. There we go. So then if we go to second, calculate, intersect, we get x is -2. And we verified. Okay, so why don't you guys, if you feel confident, you can try part B. Otherwise, just work it along with me. So here we go. Do you see I have different bases? 9 and 27 are different. But 9 and 27 are both multiples of 3, right? Or actually powers of 3. So if I rewrite 9 as 3 squared, and that's being raised, I'll put this in parentheses, to the -x plus 15. And over here, do you see 27 is 3 cubed? And that's being raised to the x. So 9 is this one here, and 27 is this guy here. So when you raise a power to a power, what do you do with the powers? Good, multiply them. So we're going to end up with 3 raised to the 2 times -x plus 15 is equal to 3 raised to the 3 times x. And now I've got my same bases. And so I can equate my 2 powers. So we'll get, whoops, 2 times -x plus 15 is equal to 3x. And then you just solve that equation. So we'll get -2x plus 30 is equal to 3x. 30 is equal to, if I add 2x to both sides, I get 5x. So 6 is equal to x when I divide both sides by 5. So my solution would be 6. So now what I want to do is I want to go to my graphing calculator and verify that. And what we'll do is we'll do the original equation. So I'm going to go to Zoom Standard first, and then I'll enter in my y equals. Okay, so we had 9 raised to the parentheses -x plus 15. And then we had 27 raised to the x. I'll probably have to adjust my window for my y as my guess. Okay, so let's do this. First we'll just let's try zoom fit. See what we get. Well, we're getting closer. So let's see. So for our x minimum, we're checking to see if we verified a solution for x. So let's just do -2 for our minimum. And max we can keep, I guess, at 10. And then the y maximum, oh, that must have exponent. Yeah. So the y minimum, let's do y minimum at -1. And the y maximum, it's going to be a pretty big number, I believe, because 27 to the 6 is going to be really large. So let's just do like 1 and make our scale like 100, I guess, for y. Let's see what that looks like. Oh, we still haven't gotten it. We got to go bigger. Okay. Maybe I went too big there. One more time, we'll delete a couple of these. There we go. That's a good one. Okay, so second calculate, intersect. And look at there. At x is 6, we got our intersection. Okay, so here we go for this guy. We're going to have to use, a little bit of fun times with laws of exponents here. So I have the same base here, but I've got these grouping symbols that are making it kind of mean. So e to the 4th raised to the x is e raised to the 4 times x, and then times e raised to the x squared equals e to the 12th. When I multiply same bases, I add the powers. So now we're getting there. So now do you see we have a single base of e on each side, and then we can equate these powers. And the thing to remember is that, once you equate the powers, you got to remember that you know how to solve equations that are exponential in form. So I'm going to get 0 on one side and write them in descending powers of x. And let's see what we get. We'll get, I think that factors 6 and 2 have a difference of 4, so that would be x plus 6 times x minus 2. That gives us a product of -12, and when you combine like terms, you'll get +4. So we have x plus 6 is 0, or x minus 2 is 0. So x is -6, or x is 2. So these are two answers, and let's check out the graph. This will be another kind of weird window. Okay, so we have E that's being raised to the fourth. Oh, and I forgot the first parentheses. Okay, there we go. And then that whole thing is being raised to the x times E raised to the x squared. So that's our first graph, and then our second graph is going to be another big number. It's going to be E to the 12th. All right, let's see what we got. Okay, so we can't see both of them. So let's adjust our window. Take away some of these zeros. Reduce the scale on y. And see what that looks like. Oh, we need to adjust our bounds on x as well. So let's see, window, x minimum should be -10. I don't think this needs to be so big. Let's delete some of these. Let's try. Let's try this, see what we get. It's our first graph. Second graph. So now what I want to do is I want to maybe do y scale of 0.1. Okay, so try zooming in. That's not helping us. Let's look at our window here. Let's do our y minimum at -1. That's looking better. Huh. Let's see. Well, I can go back to the old standard. This one's being really stubborn. I'm trying zoom fit now. Ah, gotcha. Okay, so it's a little odd, but let's go to our intersect. So our first intersection point is at x equals 2. And then, so we'll do a screenshot, a screenshot of that. And then the other one, we need to cursor more to the left. So we'll go second calculate intersection. And we need to go more by -6. I should have adjusted the window first. Well, at least it's adjusting on its own, right? Almost there. Actually. Okay. There we go. It's hard to read that there. You know, let's go to table because I'm not even seeing. Let's see. There we go. Do you see here? This one was a hard one to get on the screen. Maybe I'm just being dorky. All right. So there you have it. We have verified the solutions. So let's look at some applications. So this one interested me, especially since I fell during the summer and I had a wound. So the normal healing of wounds can be modeled by an exponential function. So A0 is going to represent the original area of the wound in millimeters squared, and A equals the area of the wound after n days. So that's our equation. It's the growth factor is negative, so that means that the wound area will decrease as time goes on. So here we go. If the wound initially has an area of 100 square millimeters, so remember A0 is the original area. So we would have, in this case, A0 is A0 is 100, and then N is 3. So A evaluated at 100 will be, nope, A evaluated at 3, my bad, will be 100 e to the negative 0.35 times 3. So we're basically plugging in for n, we're plugging in 3. So let's go to our graphing calculator. We would have 100 times e raised to the negative 0.35 times 3. So we would get approximately 34.99 millimeters squared. So after 3 days, it's shrunk quite a bit. Now after 10 days, let's see what happens. So now we're evaluating A at 10 is 100 times e raised to the negative 0.35 times 10. So instead of plugging in 3, we're now plugging in 10. So let's see what we get. I'm just going to go second, enter, and then change this to 10. And we get approximately 3.02 millimeters squared. And that makes sense, right? I mean, you would expect the wound to decrease the more days that go by. Okay. So the next time you get a wound, you can measure it, the area of it, and see what happens after each day. Okay, suppose that a student has 500 vocabulary words to learn. If a student learns 15 words after 5 minutes, the function L at t equals 500 times quantity 1 minus e to the negative 0.0061 times t approximates the number of words L that a student will learn after t minutes. So how many words will the student learn after 30 minutes? So L at 30 equals 500 times quantity 1 minus e to the negative 0.0061 times 30. So wherever I saw a t, I plugged in 30. So we'll get 500 times quantity 1 minus e raised to the Okay, so what did I plug in? I'm sorry, I plugged in 10. Second entry, I'm supposed to plug in 30. I was thinking of that last problem. 30. Okay, so approximately 84 words. 84 words. Interesting. Okay, so then let's see what happens after 60 minutes, so after an hour. So L at 60 will be equal to 500 times quantity 1 minus e raised to the negative point, what was it, 0061 times 60. So you also have to be really careful that you're in the right increment of time. So this function was given in minutes, so we're good. All right, so you can learn approximately 153 words after 60 minutes. Okay, so I think does that wrap it up? Yes, it does. I think this is like the longest section we had left. So hang in there. You're getting closer to the end of the course. All right. Have a fabulous day. Bye.